So we were looking at ignition, and then we were looking at ignition as a somewhat like a reverse process of quenching, not exactly, but you look at the numbers to be slightly different, but the processes basically have the same idea. Therefore we could now think about again like a parallel plates. What I was saying yesterday is instead of having like a global energy balance, we could actually have a local energy balance. So let's look at a different approach to do this to probably get the same results again, so or similar results. So consider a gas between two infinite parallel plates, and now what we are saying is at ignition, that's one of the criteria that we listed. So at ignition we need to have d by dx of minus k dt by dx equal to wq, where this is actually the should use a different symbol here, maybe the qr. So this is the chemical heat release or the heat of reaction, and therefore you could say d squared t over dt squared dx squared, which is, so this is the conduction heat loss, that's q, small q, and that's equal to the chemical reaction rate, right. So that's equal to so if you now assume constant k, then you're going to get minus qr divided by k. And you can now write this w dot as a e to the minus e over RT yf power p yo power q, right. Keep in mind that this q is not the same as that, so we run out of symbols pretty soon because we use kind of pretty much the same kind of symbols most of the time. We could say m and n, but that's fine. Now the reason why we have to write the w dot like this is because this is a differential equation in temperature, and the temperature shows up here. So that means when you now integrate this, strictly speaking we should think about like bringing this down here and then taking it up there and integrating and so on. Now that's of course an involved process, so let's actually try to see how we can manipulate this a little bit more. So introduce non-dimensionalization, eta equals x over capital R, that's non-dimensionalizing the length, and now let's suppose that nu stands for T minus T naught, that's a departure from the wall temperature for the gas, and let's say theta equals E times T minus T naught divided by or T naught squared. This is not the same as our Zeldovich factor because we used to have a TF, keep in mind, and so obviously then this can be written as E nu divided by or T naught squared. Now note that we were saying nu is quite small when compared to T naught. That means we are looking at small departures from T naught for the temperature near the wall, and if you have this notion, then e to the minus e over RT can be expanded about T naught as exponential of negative e over R T naught plus nu, and that can be written as exponential of minus e over RT naught times 1 plus nu over T naught, and then you do a binomial approximation. So this would be exponential of e over RT naught 1 minus actually should have a parentheses here, 1 minus nu over T naught and this should be equal to e to the capital nu over r t naught squared times e to the minus e over r t naught, right, and that means this is equal to e to the theta times e to the minus e over r t naught. Okay, now let us say let delta equal to qr over k e over r t naught squared r squared. Well, maybe again I'm mixing up symbols, so we should go back and write this as ru and ru. There are plenty of places where we need to make this correction. So and qr over k e over ru t naught squared capital R squared a e to the minus e over ru t naught y yf power p yo power q. So just in case, maybe we can just go back and put q dots there. Okay, so if you now do this, go back to your original equation. So this is where we were, and we did all these things, and so finally what you're going to get is we get d squared theta over d eta squared equal to minus delta e theta. That's really what I like about these non-dimensionalizations. You know, it's kind of like you've been to a haircutting saloon and got yourself a nice haircut, so the governing equation now becomes so looking compact, right? So for the boundary conditions, we have x equals, in our new coordinates eta equal to 0, we have to suppose that dt over dx equal to 0 by symmetry, and x equals r, which implies eta equals 1, we have to have t equals t naught. If t is equal to t naught, then nu equal to 0. If nu is equal to 0, then theta is equal to 0, right? Theta equal to 0. Now let's now do something like a linearization. So take e to the theta as 1 plus theta. That means you do a Taylor expansion and chop off things that are going a square and so on. So if you do this, then that's pretty straightforward. What this means is e to the d squared theta divided by d eta squared plus delta theta equals minus delta. So you just go back and plug e to the theta as 1 plus theta in this, and expand out and take the term with the theta to the left hand side, so that you have a differential equation that looks a lot more familiar when compared to what we are used to, what we have been having, and therefore theta equals, let's say, a1 sine square root of delta eta plus a2 cosine square root of delta eta minus 1, right? So you have the complementary part and the particular integral there, and therefore you get d theta over dx from here as square root of delta times a1 cosine square root of delta eta minus a2 sine square root of delta eta. So if you now supply the boundary conditions, the symmetry boundary condition implies that you now plug your eta equal to 0 and the sine term goes away, and then you now say that d theta by dx should be equal to 0, which is the same as dt by dx equal to 0. That means that the cosine is actually going to 1, therefore a1 should be equal to 0, and at the wall theta equal to 0, this means 0 equal to a 2 cosine, that's coming from there, cosine delta minus 1, right. So from here we get a2 equal to 1 over cosine square root delta, and theta now becomes cosine square root delta eta divided by cosine square root delta minus 1, right. So with this, what this means is we need, look at what is theta is. Theta is t minus t naught times e over this, right. So for the solution, what we are looking for is ignition. That means we need to have some ignition energy that is there, that is going to raise this temperature from T naught to whatever value that will create the reactions to happen significantly. Therefore obviously T has to be greater than T naught, so theta has to have positive solutions, right. So one of the things that we have to look for is, of course eta is a variable, so that's varying, and you have to make sure that you have to have this one for the range of etas that we are looking at between 0 and 1 should be greater than 1, right. But more than that, what we have to worry about is, so we need theta greater than 1 everywhere for ignition. More than that, we need theta to be bounded. Okay, it's one thing to actually have greater than 0, right. So more than theta just being positive, we also want to make sure that theta doesn't really blow up, right. So also the solution becomes unbounded for cosine square root delta going to 0. So if the denominator goes to 0 even in the first term, then you are in trouble, which implies that square root of delta is pi by 2, right, or you can say delta is equal to pi squared by 4, right. So if this is the case, then you don't have a steady state solution. So no steady state solution, exists for this value and above. Now unlike problems that have this kind of a governing equation, at least for the homogeneous part, where we would be looking for oscillatory situation, and eigenvalues having multiple values, right. So obviously you can say that cosine square root of delta is going to be 0 when delta is equal to pi by 2, 3 pi by 2, 5 pi by 2 and so on, but that's not what we are interested in, right. So as you now have the delta actually keep on increasing, you now reach this value and that's bad enough. We don't have to worry about the next value it's going to reach and the next value. Those things are not basically physical anymore. What we are interested in is, like, let's say the first value. Why are we interested in that? Because delta for you, what we are looking for is the capital R squared. As your size, so long as your size is less than a certain critical value, you are now going to have more loss when compared to the heating by the chemical reactions. And at ignition what we are saying is this equality happens. So this equality begins to happen for a certain minimum critical value of capital R over here, and therefore a corresponding delta beyond which ignition will happen. And again this equality won't hold good, because you will now have more heat release due to chemical reactions than the conduction at the walls, and then the reaction grows, and then you now have an ignition, right. Before the critical value of capital R, or below the critical value of capital R, and correspondingly a less than the critical value of delta, you are going to have the heat loss to be greater than the chemical reaction, therefore ignition won't happen, right. Therefore what we are basically looking for is, this implies that delta critical has a minimum value for ignition, right. Now if you go back and look at this delta, and let's not worry about how this delta is really formed, let's now begin to look at the dependencies. So looking at dependencies of delta crit, right, and this is always something that we have been thinking about. We always have to have R crit squared, and since you have these dependencies here, that's going to now have a pressure dependence show up through the concentrations. So you're going to have a P power n show up here, and of course we have a e to the minus E over RU T naught showing up, T naught, and you have a T naught square at the bottom, right, T naught squared. Now this should be depends on, so let's say equal to a constant, right. Now the constant here that we are talking about is pi by 2 in this analysis, and as I said, let's not even worry about the next values and so on, but in reality this constant is empirical, it's not exactly this. That's because we are losing a lot of things. First of all, you're kind of assuming a momentary steady state here, that this equals that at just this particular point, but there was it's a dynamic process. You have an unsteady process essentially, and then we are not really worried about the variation in the temperature with time when this ignition is happening. So we assumed a steady state process and then looked at when it is violated. So this formulation is somewhat limited in the way it is done, but the most important thing that we are looking for is the dependencies on pressure and temperature, the pressure of the system and the initial temperature of the reactants. That's what we are looking at, and therefore we simply say this should be equal to a constant, or if you now have this greater than a constant, then you will have ignition. Or if you want to avoid ignition, like for example you want to now say I have a very narrow tube and I have reactant mixture that is being sent through the tube and I want to make sure that it doesn't get ignited, then the R critical should be less than this constant value, right. So that's typically obtained empirically, the actual value of this. So here what we can see is that R crit then squared goes as 1 over Pn, sorry, P to the n, keep that in mind. And also you now have a slightly complicated T naught dependence. Okay. Now let us also now look at what's the situation if you now have like a spark ignition. Okay, so what we have done is something like a thermal ignition where we are trying to heat up otherwise, so but spark ignition is slightly different. You need to have electrical energy put in there, and spark ignition is something that's very commonly adopted in many ignition situations of practical in practical systems. So our goal here is twofold. One is looking at something like a R critical similar to this, and I'll show you that a similar dependence can be obtained by looking at the global energy balance similar to the way we were doing for the quenching. So find minimum ignition energy right. So what we are looking for is if you now have a spark that's coming up and you now have a flame that is now growing from here spherically, locally spherically, that's how it's going to happen. So strictly speaking we should be looking at a critical radius for the spherical flame that will sustain growing, propagating, instead of giving away the heat that is liberated during this ignition to the surroundings. So if you really think about this, let's suppose that, as I said long ago, you fill this room with reactant mixture, okay, and then you pray that it's not going to get ignited, and what happens when it gets ignited? Or why is it so? Is reaction going on when it's not getting ignited? That was a question that we were asking before. The answer is, according to the Arrhenius law, because it's actually at some temperature, the reactions are going on. Okay, but the reaction rates are so low that the heat release rate is so low that it's just getting conducted away to the surroundings from where it is happening, right? So therefore, what we are basically looking for is what's the energy that is being supplied by the spark that will actually ignite a critical size of this flame ball whose surface is so large now that the chemical energy release that's happening in this is sufficient to overcome the heat loss to the surroundings, right. So that's what we are essentially looking for. So the flame will not propagate if the radius of a spherically propagating flame is less than a critical value. And the idea is very similar to what we have seen so far. So that is at this stage QR dot equals QL dot, and that is to say W heat release, so reaction rate times heat of reaction, that is heat release rate, times 4/3 pi R crit squared, cube should now be equal to conductivity times 4 pi r crit squared, that is the surface area, times Tf minus T naught divided by r crit. That is to say, we are now basically assuming that locally the temperature is high, alright, but then this gives rise to a temperature fall just outside this ball, and now therefore you have a heat loss. In fact, if this is your T naught, let's do this on this side, and this is your Tf, you could actually take a cylindrical column. Let us suppose that you now think about like a hollow cylinder, that means a cylinder of a wall thickness, right. So you have an inner diameter and an outer diameter, inner radius or outer radius, and the temperature inside is uniformly Tf, okay, and now you tend the outer radius to infinity, okay. So it's kind of like a hole in the middle of nowhere, right, and then the hole is at a Tf, and far from here is actually T naught. You should now be able to do a conduction problem for this particular situation, and then try to find out what is the heat transfer at the wall, and you should be able to show that this is what it is, right. So if you do that, then from here of course you can so you can cancel this r crit here from here, and then this from there, and get a squared. So r crit squared then is like 3k Tf minus T naught divided by W dot Qr. Keep in mind, previously we had a W dot which we had to expand in terms of temperature because we are using a differential equation in temperature, but here we are not really writing a differential equation in temperature. The values of the temperature are actually placed as specific limits, therefore we shouldn't have to worry about expanding this in terms of the Arrhenius law and the law of mass action. Here we can just keep it this way. And previously we also said that this Qr is nothing but Cp times Tf minus T naught, so we don't have to worry about the Tf by T naught, but keep the Cp at the bottom. And if you now have a K over Cp, that can be directly written in terms of alpha, right. So if you now find this r crit squared is equal to alpha, similar as alpha divided by W dot. Similarly, we also had a SL squared is equal to SL is equal to square root of alpha W dot, or SL squared is alpha W dot, right. So if you now think about r crit squared is equal going as alpha divided by W dot, SL squared is going as alpha W dot, then you can directly get from here, you can see that r crit goes as alpha over SL as before. As before is during quenching, right. Now I want to caution you that you now have a number 3 here that's coming from the volume to surface area kind of consideration, but in reality we don't have this kind of number, it's more than that, right. And I'll point that out, that this was related to the penetration distance yesterday when we're doing ignition. So if you now say we are interested in the energy, so if you now say that the E ignition, the energy that the spark is going to deposit into this gas is supposed to go and increase a critical mass of gas m crit to the temperature Tf minus T naught, right. That's what this is supposed to do, this energy, right. And in fact if you think about this, this is essentially the statement of the second criterion that we wrote yesterday as a rule of thumb, and this is actually relating to the first criterion as a rule of thumb. So we are kind of applying both in stages, and this m crit now is essentially like a pocket of gas of a certain critical mass, and therefore it's going to be density times a critical volume, and the critical volume is associated with the critical radius that we are looking at. So therefore we can now plug the critical radius there. So this is nothing but 4 by 3 pi r crit squared, I'm sorry, r crit cube. You also have a density. This density is for the pocket of gas that has got ignited. Therefore you are looking at products within the sphere, right? So you need to have a rho infinity there, and Cp Tf minus T naught, and so this implies that ignition. Let's not worry about the 4 by 3 pi. Let's now begin to look at the dependence. And so what we see, because we are now looking back again at the R crit going as alpha over SL as the dependence, and therefore this depends on, keep the Cp, all right, and write your rho infinity as P over R infinity Tf, right, and keep the Tf minus T naught, all right, and then look at R crit. R crit is nothing but alpha over SL as a dependence. Therefore this is going to now go as alpha over SL the whole cubed, right, and in fact putting everything together in terms of how the alpha depends on pressure and the pressure dependence here itself and SL's pressure dependence, everything together, we will retrieve from here we could deduce that E ignition goes as P to the minus 2 for n approximately equal to 2. This is for if you now go back here, you are talking about P to the n. N is the order of the reaction. That means if you are now looking at a global reaction with a law of mass action like this, it's essentially P plus Q, right. So n equal to 2 is the order of the reaction. If you now plug that in there for the SL dependence on pressure, you should now get this, taking other pressure dependencies in this expression into account, and this is for typical hydrocarbons. Right, and this actually pretty much gives a good dependence compared to experiments, right. So if you now think about how the experimental dependence is, so experimentally it's observed that if you now try to plot your E ignition versus pressure, and of course if you now do this on a log scale, right, we should now get a straight line that goes downwards. But what we find is typically this the data goes more like this, which means this is the P to the minus 2 dependence, and the P to the minus 2 dependence is actually fairly well satisfied in the low pressure region when compared to the high pressure. High pressure you don't have this fall, so that means you do have a critical ignition still needed. I mean the ignition energy needed is more than what the pressure dependence would say. And of course that implies a kinetics effect as well. That means there is the reactions don't behave exactly the same way in terms of the global kinetics is concerned. And the other thing obviously we are interested in is the temperature dependence, and there is some data to suggest that if for the temperature dependence like for example if you now say for increase in the let's say 300 to 450 degrees C Kelvin range, right, the E ignition drops from around tens of millijoules to a few millijoules. That means we are looking at numbers like about 40 millijoules to 70 millijoules at 300K, whereas when you now go to like 450K, you need only about 4 millijoules, 5 millijoules kind of thing, right? So as the temperature, the initial temperature is increased, the ignition energy required, minimum ignition energy required is less correspondingly. But you can actually work out how this exact dependence is yourself from here. Okay, so with this we should conclude ignition, and as well we would like to stop talking about premix flames. Essentially what we have done is we have spent significant amount of time talking about premix flame deflagrations. We have not done premix flame detonations, starting from where we did the Rankine-Hugoni relations, and we saw that you have one branch is actually for deflagration, so the other branch is detonation, but essentially the idea is for premix flames, right? We were always assuming that the reactants were approaching the flame in a premix state, and then we started asking the question, how do you know what is the slope of the Rayleigh line, and that is actually corresponding to the flame speed, and so that actually turns out to be an eigenvalue of the system. If you now look at how the equations pan out, looking at how the preheat zone and the reaction zone is, then we constructed the preheat zone temperature profile and the reaction zone temperature profile to zeroth order. We just say this is a convective diffusive zone, that's a reactive diffusive zone, and then we neglect the other terms that are unimportant, like the reaction rate term in the preheat zone and the convective term in the reaction zone, and construct temperature profiles, match the slopes at the interface, and then try to get the flame speed. And then we started looking at the dependence of the flame speed on physico-chemical properties, initial conditions, or the reactant conditions, pressure and temperature, and so on. And then we looked at the flame shapes, how the flame actually gets shaped over a burner, and how it gets stabilized, and what happens to it at the peak, at the tip, when you have a flame curvature and a flow divergence effect. And then we started looking at flammability limits and quenching criteria and ignition criteria and so on. So all these things actually we have been talking about are primarily in the context of premixed laminar deflagration, right? So it's time we started talking about diffusion flames, and so now onwards for the rest of the time, or at least for quite some time, we should now be talking about diffusion flames. We are still primarily in the deflagration regime, that is, we are looking at low subsonic Mach numbers for the reactant flow, and therefore we have to go back and look at the momentum equation and find that the pressure is approximately a constant, because we are now looking at low Mach numbers and low Knudsen numbers, and therefore it just reduces to pressure, it's a constant, which means we can go back and adopt like the Schwab-Zeldovich kind of formulation, and where we have to look at the species conservation equation and the energy conservation equation with a flow field that is prescribed, unless of course you want to take into account the density variation with temperature, which will alter the flow field. And you can now look at the flow problem loosely coupled with the combustion problem, and not necessarily tightly coupled, unlike in a full compressible manner. So we will now begin to start talking about diffusion flames. Now diffusion flames is actually kind of like the classical term for flames that are essentially non-premixed. So the modern terminology for this is simply non-premixed flames. So we have to understand why we are getting these different semantic notions about this. What we mean by a diffusion flame is, here we are now saying that the reactants are just mixing at the flame, right? It's kind of like you're rushing into the exam hall and you're just studying for the exam, right? So you're really not prepared. So similarly, the reactants are not really prepared. And what is meant by prepared? Pre-paired. That means you have to actually pre-mix, right? So if the reactants are pre-mixed, then they are ready to react, and all they are waiting for is for a temperature rise to happen, and then they are going to react, right. And in a steady state situation, the temperature rise happens because of the flame that has already been established, and so as the reactants get into the flame, they get preheated and then react. That's what the flame is all about. That's how we were talking about it. But in this case, you have a flame, all right, but the reactants are just mixing at the time they are reacting, right. So when that is happening, then you have to start thinking about which is a faster process. Is it the mixing, is it going to be quite fast, or is it the reactions that are going to be quite fast? Right. Now typically in a combustion situation, what we are interested in is fast exothermic reactions, right. This is what we started talking about right at the beginning. So we are always interested in situations where we have a very high sensitivity of the reaction rate to temperature, in turn meaning a high activation energy, right, and that simply means that the reaction rates are going to be very, very fast once you got the mixing to happen, right. So this is a situation where the mixing is the one that is limiting the entire set of processes. In other words, if the fuel and air were to mix, or the fuel and oxidizer were to mix with each other, then the reactions will happen rather instantaneously or immediately, right. So mixing is the rate limiting process in case of diffusion flames, and of course the technical sounding term for mixing is diffusion. So you can say diffusion is the rate limiting process, and therefore the heat that is released from a diffusion flame is not necessarily limited by the chemical kinetics, as in the case of premix flames. So you would say there premix flames are kinetically limited in terms of heat release, whereas in the case of diffusion flames you should say it is diffusion limited, right. So you are not going to really experience as much heating than premix flames. That's essentially the idea. So here the mixing between the reactants, or mixing of the reactants, is the rate limiting process relative to reaction. Therefore the heat release in a non-premix flame is diffusion limited. As opposed to being kinetically limited in a premix flame. Hence the name diffusion flame for these, but we will see that there is some exception here. I mean, we'll just keep building this idea and then see where it falters. Okay, so at the moment the idea basically is that diffusion is the rate limiting process, and therefore the heat release is diffusion limited rather than, or the heat can be released only to the extent to which the reactants can mix than whether they can actually release by chemical kinetics, like what is the chemical reaction rate based on law of mass action and so on. So the thing that we have to think about is, are these very common? In fact, these are actually more common when compared to the premix flames. Premix flames pretty much have to be contrived many times. You have to mix, somebody has to mix the reactants, right? Whereas diffusion flames are the ones that happen naturally in nature, right? So if you want to, for example, light fire to a block of wood or something like that, that's essentially a diffusion flame that's going on, right? And candle flames are the best example, right? So the candle flame is essentially a diffusion flame. So the laboratory, if you want to now establish a diffusion flame, go back to the Bunsen burner that we have been talking about, but you now shut down the air entrainment along with the fuel at the bottom, right, and just allow the fuel to come along and have the air mix with the fuel outside. And that's a pretty good interesting experiment that you can think about. So if you now had a Bunsen burner and you now had the bottom ring open pretty much fully, and you had this orifice through which the fuel is coming out like a jet and creates a locally low pressure so that the air gets sucked in and entrains into the fuel and then mixes into this tube, and then you now have a nice conical blue premix flame, and then you now start slowly trying to move this ring so that the hole is actually progressively closed, and you are letting in less and less air, and as you let in less and less air, you are making this flame more and more fuel rich, because you just have more and more fuel and less air, so it becomes fuel rich. And we talked about fuel rich premix flames earlier in the context of stabilization, and what we understand is two things. One, as the air entrains at the base of the flame, you are going to have a enrichment of this mixture, and it's going to be closer to stoichiometric and actually get anchored much more firmly. The other thing is, for the remaining shoulder of the flame, you're going to have a fuel rich products that are coming out, and that is going to mix with the reactants and have a diffusion flame envelope, right. So ultimately, when you now close this ring completely and don't let in any more fuel, then what's happening is you have only fuel coming out, and then you have mixing of air that's happening. And typically what you should find is you now have a diffusion flame that is fairly elongated when compared to a more compact premixed conical flame, and this is going to now look not exactly shaped like a cone anymore, right. It's going to have like a teardrop kind of shape, and it's not blue any longer. It's more orange and yellowish in some pockets and so on. So it's essentially typically your orange flame. So what this means is you have inside of the flame you have all fuel, outside of the flame you have all oxidizer, at the flame you are basically having the two mix and produce products. But of course the products are free to diffuse on either side, and they are in general getting convected upwards, and of course the whole set of species are actually moving upwards because of buoyancy. That's another matter in a gravitational field around, and that's partly the reason why you're seeing this kind of a shape for the flame, and also the reason why the flame looks elongated, besides the diffusion process itself causing it to elongate when compared to a compact conical premix flame. So these are lots of these kinds of different things that are happening as you now change this from a premix flame to a diffusion flame. It's a nice experiment that for you to think about and do. So diffusion flame can be commonly come across, and we will now talk about how to analyze this next class.